For chapter 3, you already know about the groups and periods, but let's discuss more about the periodic table. In periodic table, the group numbers are written on top, group 1, 2, 3, 4, 5, all the way to group 8, which we also call group 0. Why do we call it 0? We're going to discuss that a little later. There are periods with numbering 1 to 7. Remember, the groups are numbered in Latin numbers. The period are numbered in proper mathematical digits. There are 7 periods. There are 8 groups. However, the central blue portion has not been divided into any groups. It is divided into groups, but we don't teach you those groups at IGCSE level. However, you're going to learn all of that in A levels. These are colored. They are colored differently, and the colors are written below. Let's go through that. The most reactive metals are colored as pink. This is group 1, the alkali metals, and group 2, the alkaline earth metals, which means they're all metals and they are all pretty reactive. Next up is the green portion. We call them poor metals. Right in between this green and pink is blue, which are transition elements, which are hard, strong, and dense metals. Accompanying the green are the brown ones, which we call the metalloids. Metalloids are actually half metals, semi-metals, or you can say the ones that contains both properties of metals and non-metals. We call them metalloids. Right? The good thing about metalloids is that if you notice closely, you would see that there is actually a staircase over here like this, which is drawn in bold. And this staircase actually consists of brown elements right on top and bottom of it. Except for aluminum, which is bottom of the staircase, but is not considered. So this staircase will easily can tell you that where the metalloids lie. So we have all the metals on the left of the staircase and all non-metals on the right of the staircase. The staircase is usually given in bold in color in your actual paper, but if it hasn't, it's not a big problem. Start drawing a staircase right from the boron's corner and keep taking it and marking those elements up top and bottom of the staircase as metalloids. Easy enough. So you can divide the periodic table always by yourself, even if this staircase is not bold in your copy of periodic table in the question paper. Now, the yellow ones are the pure nonmetals. Specifically, group number 7 has a specific name, halogens. Then the noble gases are the orange ones. What's not written over here is about the purple, and we call them rare elements or rare earth metals. Rare means which are present in a very small amount, right? So what we say is that we have all metals in the periodic table. That is around 75% approximately, and hardly 25% or even less than that. Sometimes we even say it's around 20% or less is non-metals, because both orange and yellow are non-metals. Brown are metalloids. The rest of the periodic table are all metals. Now, moving on, we are going to classify the elements. The first way to classify them are groups and periods. You can divide the elements into groups and periods, and it is pretty easy to locate any single element in a specific group or a period. This has been a part of past papers, but we now consider it an easy question. We don't give it to you. But if I ask you to locate anything from period 4, which is present in group 6, you will always land on one single element. Take a look. This is period 4, and this is group 6. So you land then and there on selenium, Se. So it's pretty easy to locate an element if you know its group number as well as its period number. That is not considered a part of questions anymore because that's way too easy, but still, locating elements from periodic table is something you should be quick at. Not just correct, quick, because that might take more time than what you expect. The second method of classification is metals and non-metals. We have already divided the entire table into three categories: metals, non-metals, and metalloids. We're going to discuss metalloids later at the bottom of page 57. Let's start with metal and non-metal first. Metals or non-metals don't have any specific definition, but a few set of characteristics that are opposite to one another and can always be compared. Let's go through those characteristics. And out of this table, what I usually tell my students is that this table consists a lot of exceptions. They're going to go forward and put some rules. And with most of the rules, they're going to come up with exceptions. Those exceptions have been important in MCQ papers. So make sure you understand all the exceptions and remember them. They're a part of memorization. Metals are solids except for mercury, which is a liquid. Non-metals are not solids and gases, again, except for bromine, which is a liquid, which means there are only two liquids in the periodic table. One of them is metal, mercury. One of them is non-metal, bromine. Metals boiling and melting points are usually high. However, that's the opposite for non-metals, which are often low. Metals are usually hard and dense. Non-metals are usually soft. The only non-metal that we consider very hard, or which is actually naturally the hardest substance on the planet, is diamond. Now that's an exception. All non-metals are softer than metals, except one, diamond. Their densities are often low. Metals are usually having high densities. All metals are good conductors of electricity, and that's an A. Why do we write an A over here? It's written at the bottom of the table that it's the simplest test of a metal. How metal has many properties which are listed in this table, but this is the property we call something characteristically a metal or not. Take a bulb, wire it through a switch, pass it through a battery, put it in between the metal, right in those rods or switches, and if the bulb lights up, it's a metal. If it doesn't, it's a non-metal, and that's the way we check a metal. There are other properties, but we don't go with those properties first. We always check it with electrical conductivity, and this has been a part of past papers, so make sure you prefer it too. There are poor conductors of electricity when we talk about non-metals. However, graphite is a form of carbon, which is a fair conductor. Again, an exception. Others tend to be insulators. They're good conductors of heat. Non-metals are poor thermal conductors, again, except diamond, which is not written over here, but is a part of your physics books. The shapes can be changed by hammering. They're malleable. They can be converted into sheets by simple hammering. However, non-metals are brittle when solid. Brittle means whenever you're going to apply force on them to change their shape, they're instead going to break. They can be pulled into wires, stretched into wires. If we break them from both sides and stretch them, they can be converted into wires. We call that ductility. Non-metals are not ductile. We've already said they're brittle. Most metals have silver gray appearance, except gold and copper. Remember, gold has a golden appearance. Gold is the color. Copper has a red-brown appearance. Make sure you write the colors because that's what you're going to need in papers, especially for the color of copper. Code is very simple. They don't consider it, but the color of copper has been asked in past papers, especially paper 4 and paper 6. Paper 6 the most. For non-metals, they vary in color, but they have a dull surface when they are solid. However, metals can be polished and they can have a really shiny appearance. Lastly, from this table, whenever we struck them, they make a ringing sound. So metals, this property is known as sonority, or metals are sonorous. Non-metals are not sonorous. What I ask my students to add to this table is another point. That is, metals like to lose electron. Whenever it would be about any kind of chemical reactions, metal will be the first one to lose electrons. Non-metals, on the other hand, are the exact opposite, and non-metals like to gain electrons. So that's another difference. Although the rest of the differences are actually physical ones, and this is a chemical one, but still, it would help you to contain all the differences in one place, be it physical or chemical. Are we good?
Yes, Mr.
Okay, so I'm going to erase those and move forward. So apart from metal and non-metal, there are metalloids. We also call them semi-metals. They have the properties of both metals and non-metals. So we call them metalloids. We use them for semiconductor chips, and most of the computers are made out of it. Silicon is the best example for that purpose. That's why we have a diagram on the of silicon on the next page. Let's move on to groups and periods. You already know that we have divided the entire periodic table into main group elements, but not the transition metals. And we have periods as well, 7 periods defining different elements. Every period represents the elements which has those specific number of shells filled as per its period number. By that I mean, if there is period number 4, every element in that period would have some electrons in its 4th shell, because they have a total of 4 shells, right? So we already know about groups and periods in that term, and we need to move on to the next classification criteria, which is electronic arrangement. So we are familiar with this one too. I have already taught you this. Let's go through the points again really quick. Elements in the same group have same number of electrons in their outer shell. Done with that. For main group elements, the number of group number is the number of electrons in the outermost shell. So yeah, that's pretty easy. If an element has 3 electrons in its outermost shell, that's most probably present in the 3rd group, right? Periods also have numbers, and this number shows us how many shells of electrons the atom has. So we are done with all of these properties. We shouldn't have a problem, and there are some examples over here which give you the idea that the period number and the number of valence electrons is exactly same for every group. So periodic table is not just a collection of elements. In fact, it has been strategized properly, numbered in such a way that if you learn how to take information out of it, taking information out would be a much quicker and easier task after. Make sense?
Yes, Mr.
Okay, which brings us to this diagram. If you look at it, this figure 3.6 may seem simple, but they have manipulated this figure more than any figures on the starting pages of chapter 3. Let's go through this diagram with some practice, because I'm going to take some time to elaborate this diagram, and I will be going back and forth on the periodic table to explain the diagram. I would suggest it would be much better if you open the same book, but with the previous page 56 of periodic table in front of you, and then you get to understand this table, so that even if when I'm talking about the table, you can at the same time take help from the periodic table page, right?
Yes, sir.
Now, before I move on with explaining this diagram, as you can see, this diagram has been divided into 3 kinds of arrows: blue arrows, red arrows, and white ones. Now, if you notice, you would see that the blue and red arrows are all about groups. Either they are going pointed downwards or upwards, right? White arrows actually represents 2 of them actually represent 2 different elements. There is one white arrow, however, which moves from left to right and is actually considering some changes in periods, but not in groups, because we can study the group either from top to bottom or bottom to top. The most usual way is top to bottom. And for periods, we can study them from left to right or right to left. However, the most common way is moving from left to right. Let's start with the blue arrows first, because they are the easiest one when it comes to that. Densities, melting points increase down any group. I tend to ask my students to add boiling point to this point as well. So you can add boiling point to this point. However, although this point seems really simple, there is an exception to this point. What's the exception? Let me take you to that exception first so that I can show it to you. The physical properties of alkali metals also change as we go down the group. The melting points become lower while the density of the metal increases. So this is an anomaly. Anomaly means odd behavior, different, where the whole periodic table accepts this arrow, group 1 does not. In case of the entire periodic table, the densities increase down the group, so do the melting points or boiling points. But in their case, just for this specific group, this line, only this one, group 1, their melting and boiling points are not going to do the same like the rest of the periodic table. How? Let's take a couple of examples from the actual periodic table. So moving back to page number 56, taking a look at this periodic table, this piece of information gives us the idea that copper is less dense or has less melting point than as compared to gold, right? Sulfur has lower melting points and density than selenium. However, potassium is going to have a higher melting point and rubidium is going to have a lower melting point because group 1 behaves differently than the rest of the periodic table in terms of melting and boiling points, but not in terms of density. So if I talk about density, I say it increases from top to bottom in a group. In case of melting point, it also increases top to bottom in a group. In case of boiling point, it also increases top to bottom in a group. That goes for all groups except group 1, which is going to behave differently. In which case density would increase, but melting and boiling points will not increase. Instead, the opposite would happen and they would decrease. Are you good with these examples? Make sense?
Yes, Mr.
So if you ever need to compare any two elements, this kind of questions require you to just move back and through the periodic table and as per your understanding, answer the questions. And you can obviously come up with one element which has greater or lower density or melting or boiling point, whatever that has been asked in the question. Let's move on to the second blue arrow. If you move from top to bottom, atoms get larger and more metallic. Now, atom get larger is something that we can easily understand. For example, in period number 2, we have lithium in group 1, that is period 2. If we talk about period 3, that is sodium. Period 4, that is potassium. Period 5, that is rubidium. So, if you go down the group, this one would have 2 shells, and this one is supposed to have 5 shells. So of course, the size of rubidium is bound to be bigger than the size of lithium because the atom is larger, having more shells and more electrons filled into it. But what does that have to do with more metallic nature? When we were discussing the properties of metals and nonmetals in the previous table, I asked you to add a point. That was about loss of electrons in case of metals, they lose electrons easily, and gain of electron in case of nonmetals, they gain electron easily. So how come they are more metallic? Let's first look at the periodic table. It's actually pretty easy to understand that way. If you look at the periodic table, you would find that there are some groups which start off on the top, like group 5. It starts off with 2 nonmetals, then there are 2 metalloids, but still at the bottom of the periodic table, we have a weak metal. Almost the same thing happens with group 4. It starts off with nonmetals or metalloids, but there are metals at the bottom. So if you go towards the bottom of the groups, you would see that there are many groups which start off with non-metals, but they do not necessarily end on non-metals. So as we're going down the group, the metallic character is increasing. That's why in group 4, the first element is a non-metal, the next two are metalloid, and the last two are actually metals. So that's what more metallic means. This also means if you need to compare any two elements on the periodic table, you can easily answer. For example, iron is less metallic, ruthenium is more metallic. Calcium is less metallic, strontium is comparatively more metallic. Bromine is less metallic, although that's a non-metal, but iodine is somewhat more metallic than bromine, although both of them are non-metals. So you can always compare any two elements. Anyone above is less metallic and anyone below is more metallic. I hope that explains the second blue arrow. Does it?
Yes, Mr.
Moving on to the red ones. Now, for the first red one, you would see that it talks about metals getting more reactive down the group and non-metals getting more reactive up the group. Cesium is the most reactive metal, useful and available in useful amounts, and fluorine is the most reactive non-metals. So if anything becomes more metallic as we go down the group, so the most metallic stuff would be present at the extreme bottom, or least metallic or most non-metallic should be present on extreme top, right? So this one becomes the most reactive metal, and especially in good amounts. Francium is more reactive than cesium, but we hardly have 17 atoms of francium at a time in the world. As it is radioactive, it keeps on decaying or disintegrating. So we talk about cesium because it is at least available in the amounts where we can use it for good purposes. And the exact opposite is fluorine. It's on the top of group 7, and this one is the most reactive non-metal. So the reactive non-metals are on top, the reactive metals are at bottom. This is because the metallic nature increases down the group. Make sense?
Yes, Mr.
So apart from these blue and red arrows, we have another white arrow over here. Atoms get smaller and less metallic. Less metallic is something that we can easily explain. Every period starts off with reactive metals, then it has hard metals, weak metals, metalloids, but periods usually end in non-metals. So of course, when we are moving from left to right, which is the usual way of talking about a period, you would notice that the metallic character decreases in such a way that every period ends at a non-metal. This is pretty much of a good symmetry to understand. How come atom gets smaller? This is something that requires understanding. Let's take the example of period 2. It starts off with lithium, and the structure of lithium is in such a way that there are 3 protons and there are 3 electrons outside, 2 electrons in the first shell and 1 electron in the second shell. This is the structure of lithium, which is actually the first element in the period 2. If you move in period 2 and you go to the farther end, you would see neon over here. Neon has 10 protons and its first shell has 2 protons and its second shell has, my bad, my poor drawing skills, its second shell has, doesn't look like a circular shell at all, has 8 electrons. So how come neon is smaller than lithium? The logic's pretty easy. 3 protons are trying to attract 3 electrons, so the attractive forces are not too strong to bring that electron as closer to the nucleus as they can. However, here the attractions are pretty increased, and because 10 protons are subtracting 10 electrons. So they can actually call the electrons in or push them inwards, causing this entire atom to shrink. Hence, neon has a smaller size as compared to lithium. Are we good? So that's how atoms keep getting smaller step by step in the same period. For example, scandium would be a bigger atom than chromium, which would be a bigger atom than cobalt, which would be a bigger atom than zinc, which would be a bigger atom than selenium. As soon as we keep moving on, the atomic size decreases from left to right in a period in periodic table. I hope that explains it, does it?
Yes, Mr.
So this clarifies the whole table. And you can even do some practice questions yourself by looking at the table, trying to memorize it, and then going back to the periodic table page and comparing any two elements for properties, any two. That would give you a pretty good idea how this periodic table works with this table in correlation. Now, right after this topic, we have trends in groups. We start with group 1, the ugly metals. If you take a look at this, you would see many detailed points over here. What I ask my students from the perspective of past papers, you would notice that they either tend to ask the physical properties of group 1 at a time or chemical properties of group 1 at a time. But those properties are written here in a mixture. So what I ask my students is to keep numbering those properties as first physical property or first chemical property, so on and so forth. That way, you can easily answer a specific number of physical or chemical properties if have been asked by the examiner. Let's start from the top, and we're going to go through every line because that would easily make us capable of marking the physical and chemical properties. For example, he starts off by saying that they are known as alkali metals and they are soft solid, which is the first physical property, and I'm going to write 1p as first physical property. They have relatively low melting points, which is the second physical property, so I'm going to mark it with 2p, and low densities, which is a third physical point, so 3p. They're highly reactive and stored in oil to prevent them with reaction or with oxygen and water vapor. Reaction with oxygen is first chemical property. Reaction with water vapor is the second chemical property. When freshly cut with a knife, all of these metals have light gray silvery surface, which is its color, and it can be considered as a fourth physical property. But it quickly tarnishes, becomes dull because it reacts with oxygen, which is a continuation of the first chemical property. Reactivity increases down the group. All alkali metals react with water to form hydrogen and alkaline solution of metal hydroxide. We can call it as second chemical property. So this is just an extension to the previous work. The reaction range from vigorous in case of lithium, and you must understand these adjectives because they are very important, to explosive in case of cesium. Now he has just used 2 over here. I hope you remember, and you might have seen a YouTube video where they pick group 1 elements, pick blocks of them, and throw them into a pond of water from afar so that there are no security issues and they can also judge. So you can always go on Google or YouTube and search for the video reactions of alkali metals with water, and that will give you a very good idea of how you can put them with different adjectives. However, that is also explained in the start of chapter 8. So I'm going to correlate and directly jump to chapter 8 to give you an idea what we are talking about. There you go. Reaction with water. Lithium reacts steadily, sodium strongly, potassium violently, Even if the equations is almost same except for the symbol of group 1 element, take this Li out, put Na in, and you'll have the equation for sodium. Or take this Li out and replace it completely with K, you have the equation for potassium. You'll see that that's the same equation. Tarnishing is a process in which the shiny layer, after reacting with oxygen, changes its color. But that happens slowly with lithium because its reaction speeds are slow, stronger quickly with sodium because they are somewhat fast, and very quickly with potassium because they are very fast with potassium. So that gives us a very good idea of increasing reactivity, the point we actually started off with, right? However, I wanted to emphasize on these adjectives: steadily, strongly, violently, or explosively, or slowly. So if you remember these adjectives, you can always come up with comparison of different processes. Make sense?
Yes, Mr.
However, we're going to stick to just reactions with water and air over here. Let's get back to the page we started off with. Okay, so this was the reaction with water. Now he talks about francium, which is in group 1, which is radioactive, very rare, half-life of 5 minutes, and decays too quickly for us to store. And the 17 atoms of francium are in existence at any moment, and this is so rare that we cannot put it into some good use. You already know that melting point or boiling points become lower. For the rest of the periodic table, it goes higher. Only for group 1, it goes lower. Let's go through a revision quickly. Alkali metals of group 1 are the most reactive metal that occurs. They're known as alkali metals because they react vigorously with water. They produce hydrogen and an alkaline solution. That hydrogen usually catches fire, so it burns on the surface. But that happens only with the ones that are vigorous. Here I'm talking about rubidium, cesium, or to some extent potassium. They produce hydrogen with an alkaline solution. That's about it for group 1. So you have the physical and chemical points that you already have separated. So I think you can easily discuss that. Okay. Any questions before I wind up the class?
No, sir.